Dislocations. As you are looking at the picture, everything seems somewhat uniform. But once you start drawing lines along the atoms, you begin to find the dislocations. A dislocation is where the atoms are out of position in the crystal structure. These dislocations allow for slip and plastic deformation to occur.
You can see in this video an example of what is called dislocation motion. The dislocation can be seen here on these rows. And where the bubbles move, it shifts within the lattice. The thing that is happening is that when the bubbles move, the rows that are uneven, forming the dislocations, cannot shift evenly. So they bump each other over a space, making the appearance of a dislocation motion.
Beukers vector. The Beukers vector is denoted as B. They represent the magnitude and direction of the lattice distortion. The Beukers vectors are easily seen with the previously mentioned dislocations. This piece that is overextended in the square is known as the Beukers vector.
A look at this picture in general, you can see that there are groups of atoms that don't quite match up with each other. For example, this group right here, as well as this group. Or like this group and this group. And what will happen is if you draw lines between these are called grain boundaries because each group can be referred to as a grain, so hence grain boundaries. And there's two classifications of grain boundaries. There are high angle grain boundaries and low angle grain boundaries. And what sets them apart is the angle between the boundary and the angle of the rows of atoms coming in. So if you look at this one over here, if you draw a line following that row of atoms and then the grain boundary, you have an angle that's, looking at it, probably roughly between 60 and 80 degrees. Generally, the differentiating point between high angle and low angle grain boundaries is about 15 degrees. So if you look over here at this one, you can follow that row of atoms out, and that's much smaller, as you can tell. I didn't quite draw it right, so it looks like it's more than 15, but yeah. And one of the unique things about low angle grain boundaries is you can also look at it where we have a dislocation right here and a dislocation right here, and essentially they're low angle grain boundaries are where they were growing together closely, but those rows of atoms can't quite continue on in the same crystal structure, so every once in a while you have a half row of atoms where it has to stop, and that's where the angles readjust along that grain boundary. Grain boundaries that is really fun to know is when dislocations get moved throughout the crystal structure, say by smashing it with a hammer, like in blacksmithing, those dislocations will move, but then they'll get caught on these grain boundaries and they won't be able to move over because if you think about it, it's a half row within a grain that's shifting, not a half row jumping from grain to grain. So these dislocations will start to pile up along these grain boundaries, and this results in higher stress because above each vacancy, so like we have the extra half row here, and those dislocation, so we have the extra half row here, and then that one coming in and the other one coming in. So above it we have compression where these are starting to like kind of push together, and then down here it's pulling it apart. So when you get all those areas of tension and compression mixing together from multiple dislocations, then you start to end up with actual crystal structures, say in a sword. Then you get areas where it's much harder and it's tougher, so which can be nice when you want it to stay sharp. And that's something unique that happens with that dislocation stack up, as it can be called.
So one last thing we can see in this video is the interaction of dislocations and grain boundaries. This is pretty hard to see without slow motion, but if you look really closely, you can see that when dislocations move into grain boundaries, the grain boundaries act as traps or sinks for dislocations. The reason for this is that bonding is more irregular around the grain boundaries, as we said before. So having a dislocation there will make less atoms unhappy than if it was in the middle of a crystal lattice. And one outcome of this interaction is the dislocation stack-ups as they all get trapped in the grain boundaries, and that was explained earlier.
Vacancies are described as open spaces within a crystal lattice. The best way to visualize this is by using bubble rafts. Here we can see that the bubbles all line up together fairly well, except for there is a hole. The alignment of the bubbles represents the crystal lattice, while the hole represents the vacancy. This same thing can happen to atoms within a crystal lattice. Interstitials are spaces in a crystal lattice where an atom has crammed itself into a spot that atoms comprising of the lattice cannot fit. This picture here shows a bubble raft with a tiny bubble wedged into the space between the bubbles. The other bubbles around it would never fit in this space, but since this bubble is much smaller, it is capable of fitting into this space. Atoms of different sizes will do the same thing inside a crystal lattice. When a small atom is able to occupy a spot that is too small for the other atoms, we call it an interstitial.
Now, another phenomenon we can observe with these bubble rafts is how grains react to stress. So in this video, we are pulling and pushing against the bubble raft, and you might expect all the bubbles to kind of just collapse into one grain, but if you look closely, you can see the separate grains sliding past each other. So the reason for this movement is that the bonds within each grain, they're like really happy with being bonded in this crystal structure, and the bonds along grain boundaries are much weaker. So if you apply stress, it is much more likely that these grains will just slide past each other instead of mush together.
Drawbacks of using bubble rafts to represent structures is generally either you'll get a ton of variation in the size of bubbles, or you'll get like a single size of bubbles. So it's really hard to create something like the rock salt structure, which we attempted here, unless you have something that creates two different size bubbles equally and those bubbles are strong enough to not pop. You can generally do that by adding some glycerin, but that's less important. So for example, like here we have the larger anion, so this would be like the chlorine in rock salt, and then the smaller cation, so this would be like sodium. And we were able to do it with a few. Wish we could mix these together better. We have almost a unit cell, but not quite. So this isn't the best example, but it goes to show that you can represent different crystal structures that don't require just one size, but they require multiple sizes. It just requires some extra skill in making the bubbles and mixing them that we were not able to achieve precisely ourselves. Thank you for watching. Bye.